Before we solve our next separable differential equation, I want to do a quick review of some of the algebra we're going to need. We're going to have to algebraically undo a logarithm, a natural logarithm, and an absolute value bars. And maybe we haven't thought too much about what math we do to undo those functions. So there's an example here, and there are a couple like this in your little textbook assignment at the end. I want to isolate the y, and the equation I have is the natural log of the absolute value of y minus 1 is equal to x squared plus 5. So what is it that undoes a logarithm? You can see that the y that I'm trying to isolate, it's not by itself for a couple reasons. It's having 1 subtracted that's inside absolute value bars, and that absolute value expression is being natural log. So we're going to have to undo sort of from the outside in. Our first job is to undo that natural logarithm. Well, a couple ways to think about it. Exponentiation, so making something an exponent, undoes a logarithm. And the base for the natural logarithm is e. So one way to think about doing this is to make both sides of that equation exponents on the base of e. So I might write e to the natural log of the absolute value of y minus 1 is equal to e to the x squared plus 5. Another way to think about it, which you might remember from your study of logarithms earlier, is think about rewriting that equation in exponent form. So that says the natural log, so log base e of absolute value of y minus 1 is equal to x squared plus 5. If that's logarithm form, then exponent form says e to the other side, so e to the x squared plus 5 is equal to the absolute value of y minus 1. So this here is the power. The answer to a logarithm is the exponent, and the base in this problem is e. So you could have rewritten this as e to the x squared plus 5 is equal to the absolute value of y minus 1. Typically, you're going to see in textbooks that they're going to use this upper version more often, possibly just so that the y ends up on the left-hand side, although it's not a big deal either way you think about it. So now that I have made both sides the exponent on a base of e, the e and the natural log cancel each other out. So on the left-hand side, I will have the absolute value of y minus 1 is equal to e to the x squared plus 5. Now, how do I undo absolute value bars? So y minus 1, it's either the case that y minus 1 equals e to the x squared plus 5, or y minus 1 equals the opposite of e to the x squared plus 5. So we actually undo absolute value bars with a plus or minus sign. So y minus 1 is equal to the positive or negative e to the x squared plus 5. And then I have one last step, which is to get y by itself. I'm going to add 1. Typically, you'll see the 1 is added in front of the plus or minus sign, although that's certainly not required. So here, y is equal to 1 plus or minus e to the x squared plus 5. And we're going to see how this next example combines that trick we used in the last problem, where we rewrite e to the something, where we split up that exponent into two separate factors, and this that we just did to isolate a y that's involved in a natural log expression. So here we go, our first separable differential equation that's going to involve a natural logarithm. I have dy dx is equal to 5y. I'm going to try to get all the x terms on one side and all the y terms on the other side. My first step is to multiply both sides by dx, and then to divide both sides by y, because I want the y to end up on the left-hand side of the equation. I'm going to end up with dy over y is equal to 5 dx. On my next step, I'm going to integrate both sides. Once I have the variables separated, I'm going to integrate. And here we go. We just learned this one the other day. the antiderivative of dy over y is natural log of the absolute value of y on the left-hand side. And that's going to be equal to, the antiderivative of 5 is 5x plus a constant. So how is it that we can get y by itself? We're going to go through that process we just went through. We are going to make both sides of this equation exponents on a base of e. So I'm going to put this e here. This process, the actual term for it, is called exponentiation. Well, e to the natural log, those functions cancel each other out. So I'm going to scooch me out of the way. And my new left-hand side now is the absolute value of y is equal to e to the 5x plus c. So remember that little trick we used in the last example. We had e to the x minus y, and we rewrote that as e to the x over e to the y. So here we're again going to use a rule for exponents that you'll probably remember from Algebra 1 or Algebra 2 to rewrite this expression on the right. The absolute value of y is equal to e to the 5x plus c could have been e to the 5x times e to the c. Because if I multiply together two powers that have the same base, I can add the exponents. So see how if I multiplied e to the 5x times e to the c, I could say, oh, that's the same as e to the 5x plus c. So I've just undone that process. And just notice here, it's the last thing you have to notice, e to the c, e is some constant, c is some other constant. If you raise a constant to a constant, you just get another constant. So you'll find typically in textbooks and in other places that you might read when you talk or think about calculus, frequently you will see this e to the c replaced with another letter, another variable to just stand for another constant. If you've worked with exponential equations before, and I'm sure you have in Algebra 2 and Pre-Calculus, you have seen a big capital A. And that's typically what we use. So in here, the absolute value of y is equal to a times e to the 5x. That's an x. Now, do you have to go through this actual process? No, I think you can actually solve this problem without recognizing that e to the c is a separate constant that you could write here as a multiplier. But I want you to know what you see when you see this in the textbook, because that's how typically this is done. So the absolute value of y is equal to a times e to the 5x. My next step is to figure out what a is. For the other separable differential equations that we solved, I took a moment and I stopped and I figured out what c is. So that's kind of what I'm doing here. I'm going to use this initial condition. So the absolute value of 2 is equal to a times e to the 5 times 0. Well, 5 times 0 is 0, and e to the 0 is 1. So the absolute value of 2, which is 2, is equal to a. So let me write my next step. I'm going to go back to where I was, which was here, and say the absolute value of y is equal to 2 times e to the 5x. So we're super close here. I have y, the absolute value of y is equal to 2 times e to the 5x. So to get y by itself, I just have to check here, positive or negative 2e to the 5x. We have that similar problem we ran into before, which is now that I've put a plus or minus sign in front of my the right-hand side of my equation, it's not a function anymore. So I have to actually make a commitment to whether I want to use the plus sign or the minus sign. And that's going to be my last step. So all I want to check now is my initial condition says that if I plug in 0 for x, I should get positive 2 for y. That makes it clear to me that I want to choose the positive version here. So positive 2e to the 5x. So that's my final answer. Notice I go through this process of checking. if I plug in 2 for y, that should equal positive 2 times e to the 5 times 0. So 2 does, in fact, equal 2 times 1. That works. This one, why don't we go through the process of actually taking the derivative and see if we get 5 times y is the derivative. So if y equals 2e to the 5x, dy dx would equal 2 times e to the 5x times 5. And notice that dy dx, I could rewrite this here. I could write equal to 2e to the 5x. What could I write in place of 2e to the 5x? Well, notice that 2e to the 5x is equal to y times this 5. So dy dx does in fact equal 5y. Proves that we had the right answer up here.